Topic is AVL tree deletion. Now, if you see carefully, AVL trees are basically binary search tree. We have to first start up with the similar way we delete from the deletion in binary search tree. In the same way, initially we will be performing that deletion from the AVL tree. Like for if you're just taking the revising the concept of deletion in BST, were three cases. The node to be deleted has got no child node, the node to be deleted has got one child node, and the node to be deleted has got two children. So these are the cases of deletion in binary search tree. So it's the same will be applicable initially to the AVL tree also. Now if you want to delete 62, 62 is a node with zero child node, that is no child node. In that case, what you have to do, you have to merely set the respective next left or right pointer of that parent node equal to null. In this case, right of 50 will become equal to null, and we have to free this node with 62. That is, a node to be deleted has got no child node. Second case is this is the output after deletion of 62. Second case is the node to be deleted has got one child node. In that case, what we have to do, we have to just set the pointer of the parent of the node to be deleted as the pointer to the its child node, because it has got only one child node. That means if this is a parent, this is grandparent, and this is grandson of that, the grandson will take the position of its parent while deleting. This node will be freed and 44 left will become equal to 32. Now considering the third case where your child node to be the node to be deleted has got two children. Say I want to delete 78, now it has got two children. Now there were two cases for that. Find the in-order traversal of this tree. In order traversal, find the in-order successor of the node to be deleted. In-order successor for the node to be deleted, like either successor or predecessor. You can replace it with either of that nodes. That means 8 node which is to be deleted can either be replaced by in-order successor or by in-order predecessor. That is your choice. You can do it by your own way. Now let us suppose if we are replacing the node to be deleted 78 by its in-order successor. So what internally is being done, this in-order successor value is being copied to the node with the node to be deleted. This node remain as such, thus the value is being copied, and actually this 80 is being deleted from this side. That means implicitly, no doubt, we are deleting a node with two children, no children, but indirectly we are deleting a node with one child node actually. So the in nutshell, if you say BST deletion internally only have basically two cases, one child and no child case internally. Even two children case are being reflected as one or zero child node. Now in this case, your 84 left will become equal to 82. This is the output after deletion of the node 78. Now after these three cases, what is special inside AVL tree? Once that respective node is being deleted, now in this case, if you can carefully scan the node, if you want to delete 78, this 78 value is being replaced by 80. Indirectly, this 80 is being deleted. What you have to do in AVL tree further, now deletion of this 80 is going may disturb the balance factor of its parent node. So what we have to do, once the node has been deleted, try to travel upward and find the balance factor of all the respective nodes coming in their path. So balance factor of that will be calculated. If the balance factor of its ancestor, any of its ancestors is disturbed, that is it is other than -1, 0 or 1, we have to perform the respective rotations just to balance that binary search tree after deletion of the node. Now, what is the special about this thing? Now, if you just recall the concept of insertion, in insertion in AVL tree, when inserting a new node, try to change the balance factor of any of its ancestors node going traveling in the upward direction one by one. In that case, you have to perform respective rotation. You can perform either left rotation or right rotation, that is called a single rotation, or double rotation, LR rotation or RL rotation. That means only single rotation, either left, right or LR or RL rotation. These are single, one rotation will be sufficient Out of these 4 rotations, one rotation will be sufficient to settle down the property of AVL tree. But in case of deletion, even after rotation, this may happen. After rotation, this may further the new rotated AVL tree may disturb the balance vector of any of its ancestors also. That means once we have performed a rotation, you may have to perform other several rotations till you are reaching at the root node. That means we have to perform multiple rotations in deletion. In contrast to insertion, whereas in insertion, just one rotation out of these 4 rotations have to be performed to balance the tree. One more thing is then this is just like in the insertion, the complexity of deletion of the node is also order of log of n, that internally is equal to the height of the tree. Now just remember, just like the rotations, a left rotation, then right rotation we did in the insertion part, LR rotation, RL rotation, the similar way the same rotations will be used for deletion purpose also. Just let me summarize the rules of that. What are the basic rules for that? Let us suppose the node to be deleted. What's the node we have deleted? We performed a binary search to deletion, and the node which has been deleted, try to find the balance vector of its immediate parent node, the node which has been deleted, because deletion of the node may disturb the balance vector of immediate of its parents. Try to find the balance vector of the node. If the balance vector of the node or any ancestor of that node, if it is being disturbed, let us suppose the disturbed node which has become the pivot node by traveling up from the deleted node, let that balance vector of that node whose balance vector is disturbed, it can be either +2 or -2, anything can happen. This is also called pivot node. Let that be a pivot node. After pivot node, try to find there might be 2 children of that node, because we are dealing with binary search tree, because of binary nature. Try to find the node which has got larger height. Let us suppose there are two heights of the tree, and larger height is in the right subtree. That means capture that right child. In that case, the child with larger height should be captured. Now this is the child with the larger height, so you will be capturing the larger height child. Let the child name is y child, which has got larger height. This is the node, pivot node, which is being whose balance vector is being disturbed, and pick a child with the larger height. This is the larger height child. After that, there might be some left subtree of that child and right subtree of that child. And after that, pick the child with larger height. So in this case, the larger height child is leftmost child. So what you have to do, this is the concept. Pick the larger, let that name that child as X child. Now there are 3 targets. One is called pivot node, and it has immediate one child which is of larger height. Immediate child of that is Y child, which has got larger height, and further there is the immediate child of Y which has got larger height. Now there are 3 cases which are possible. Either this can be the case, the pivot node, larger height child is lying on the left, and pivot and child with larger height that of y is, say, it is x. In this situation, because it is left heavy, we have to perform right rotation. This case, left case, that means y is the left child and of x, and x is the left child of y. Remember that we have to pick a child of larger height child only. Similarly, another case can be your larger height child of pivot node. Let us suppose it at the y position, and larger height child of y is also residing at the right position. Let it be x. Then we have to perform the left rotation, single rotation left. Third category can be if larger left child is of y is towards left, but larger child of y is towards the right, that is x, like in this direction. In that case, we have to perform 2 rotations. One is towards y, left, this because it's left to right is there. This is LR rotation. First will be left towards y, and then right towards z, that is pivot node. This is called LR rotation. We have to perform double rotation. Fourth category can be your z and larger child is, let us suppose, toward right, larger height child, but the larger height child of y, let it be towards x. In that case, this is right and left. RL rotation will be there. First right rotation will be towards y, about y, then then left rotation will be towards z. Next, second rotation. This is double rotation, just like we did in the insertion part. Now let us take an example. Right rotation case means the pivot node is z. Now if you carefully scan, these are subtrees. This is just for the demo purpose. There is a left subtree and there is a right subtree. If you carefully scan, out of this, larger height child is that of y. The y will be chosen. If you carefully scan it further, if you consider the further subtree of the child y, left child will be left subtree will has got larger height. Say right subtree has got smaller height. Then x will be in this direction. Larger height child will be of that y will be x. This is a case of z, y, and x. You have to perform right. This is left heavy. You have to perform right rotation about z. So y will come at the upper end. X will be copied as such, and this terminology, and T3 will be taken as the left child of Z, as we did in the insertion part. This is right rotate about the about Z node. Second is left rotation. Left rotation will occur when the pivot node has got right child, which is heavy, right heavy. This, if you see the height of this is right heavy. This is the y component, and this further for y, the child of y, this x is, this subtree is of larger height. This has got, x has got larger height. So the concept of this is z, y, and x. We have to perform left rotation about z. So this will become the final structure after rotation about the z axis, z node. Now coming to the next portion, that is double rotation. When it will occur, double rotation, like in this example, LR rotation will be in this case. When there is for the pivot node, there is left subtree. This left subtree has got more height. Obviously, this will become y. And going to the this further, this right subtree, if you go for the child of this, out of these two children, x has got more height. So we'll pick this x here. So if you consider this, the case will be z, y, and x. That means larger height child will be y immediate of z, and larger height child of y will be x, which is of immediate of y. Now what to do in this case? This is left right case, LR case. Left, then right. For LR case, first rotation will be left towards about that of child node of the pivot node. This is the pivot node, that about y. After this, second rotation will be right about the pivot node, that is a z node. So left about y, so you will be getting the output like this after rotation about y, and right about z after rotation about right about z. This is the final structure. Now similarly, RL rotation, this in this case, this will be the case when there will be right y will be of larger height, the child of y z, and then there will be x, which will be the child of y, which will be of larger height. What to do this in this case? There are two rotation. First rotation will be about that of y. That will be, this is RL case, the right rotation about y. Then left rotation about the pivot node, that is z. Left rotation about the z node. So this is the final structure after rotation. So you have to just remember these four rotations, where to apply what. Let us take example, deletion of 5. If you are deleting 5, earlier this was the AVL tree because every node was having balance vector within the range of -1, 0, and 1 only. After deletion of the node 5, what will happen? The balance vector of this node 20 has been disturbed. Now carefully scan in which case this system will now lie. This is the Z node which is to be whose balance vector has been disturbed. If you scan the difference of these two, this 35 is the immediate node. That node is y node, which is of greater height, and further moving further out of these subtrees, the height with larger height child, either 25, 40 is the larger height, so this will become the node x. Now what you have to do, this is z, y, and x. You have to perform left rotation about z. So left single rotation about z will lead to, that means left rotation about 20, that was the z node. This will lead to this structure. 35 will come at the upper end, 20 will go as such towards the right, this direction, and the left of 35, this substructure, will be taken care of by right of 20. This is a single rotation which has been performed. Now there are other more examples. Say deletion of A. If you're deleting A in this case, this will lead to this as a pivot node because its balance vector has become now equal to -2. If you carefully scan, immediately the child of this will become Y because it's the only node which has greater child height. This will become X, only node with the greater child with the height greater than that of with the greater height. So what you have to do, this is a case of right then left. This will be right RL rotation, R right rotation, first rotation toward about the child node, that is Y, then left rotation about the pivot node, that is Z. So first right rotation about the child, that is Y, will lead to G, H and I. Then second rotation about G, this will lead to H, G and I. So this will be the answer after double rotation. Now coming to the next part, let us suppose we are deleting the node L. So there are two ways, because it has got two children. You can either replace this L by in order successor or predecessor. In this example, what has been shown, they have replaced the same by its in order predecessor, that is I. After copying the value and deleting I from this, we got this structure. Uh, Luckily, this structure doesn't have any AVL tree balance vector being disturbed. Now moving further, deletion of G. Now deletion of G will lead to disturbance of the balance vector of the node I. If you carefully scan, the child with greater height of I is either H or R. Out of these two, R is a child, that this is Z node. This is a node, that is the Y node, which greater child node. Out of these, now remember this thing, out of these two children node of Y, that is O or T, both have got same height. So which one I should pick as X, either this or this? In case there is a tie, where that means both the nodes have got same balance height, in that case what to do? Always choose, in this case, single rotation. If I am choosing this as a child X, then rotation will be ZYX. If I am choosing this as a child, in that case the rotation will be Z, Y and X in this format. This will lead to double rotation. This structure will lead to single rotation. Always go for single rotation, because single rotation leads to less computation. So I will be choosing this case, the new child node, as X, not this very X. Nevertheless, they both have got same height. I'll be choosing this as X as the node with the for the consideration purpose. The output will be ZYX. This is left rotation about Z will be done. R will come at the upper end. Left rotation about I will make this tree going downward, I and H, and left of R will be taken care of by the right of the I. Then deletion of O. Deletion of O doesn't changes the balance vector of it, will directly deleted. Then deletion of R. In this case also deletion of R, we are replacing it by in order predecessor. So M is being replaced. No balance vector has been disturbed. Deletion of I, in this example also no balance vector has been disturbed. Taking one more example. Now in this case no rotation is required to perform, because the balance vector after deletion is not being disturbed. This is another example. So deletion of 10. So deletion of 10, here in this example we are replacing 10 by its in order successor. So 14 is being copied here and 14 is being removed from here. So after removal, this is the new tree structure which has been binary search tree which has been made after deletion of 10. Now if you carefully scan, the balance vector of every node is within the range of -1, 0 and 1. No need to perform any rotation in this case. Second example is, let us suppose we are deleting 4 in this structure. Deletion of 4, this will lead to this structure and the balance vector of this node has been disturbed, that is 10 node. Now this is a Z node, pivot node. What we have to do, we have to capture the immediate Y node, that is the child of the Z, which has got larger height. If you scan, this is smaller height, this 20 has got larger height. We'll pick this as a Y node, and further this we have to perform out of these two, both 15 and 30 has got same height. We will picking the rightmost because of single rotation case, that the Z, this will become your X. So Z, Y, X, this structure is there. You have to perform left rotation about Z, that is about 10. You have to perform left rotation. This is the answer after this. Now there are some cases also where we have to perform multiple rotation. We'll discuss this one by one. The deletion of 4 in this case, deletion of 4 will make this as a pivot node. Now considering this as a Z node, Immediate to this is will become your y node of greater than height, and this is the node with greater height. This will become equal to x node. 30 won't become x. 15 become equal to x. This is the concept of z, y, and x is double rotation. First rotation, this is right and left RL rotation. First will be right rotation about y, that is about 20 first right rotation. Then rotation will be about the next rotation will be about your z, that is the node 10. The first rotation will be about your the node y, then will be about pivot node, that is nothing but z. The first rotation about right rotation about y will lead to the structure. 15 will come at upper end, 20 and 30 will go downward like this. This is the partial output which you can carefully scan. After this partial rotation, the second rotation will be about the pivot node. Pivot node was 10 node. That was a left rotation about pivot node. So that what will the structure will become? 15 will come at the upper end. 15 will come at the like left of 40 was there. 15 will come at upper end. 10 and 5 will go in this direction, and 15 left, that is 14, will be taken care of by 10, and 20 and 30 remaining will remain the same. This was the structure. This is the structure after rotation. So just see carefully, after even after double rotation, after deletion we perform a double rotation, like in this double rotation RL was being performed. Even after rotation, the balance vector of the predecessor was still being they're being disturbed. That means in deletion we have to perform several rotations also. Now in this case, if you carefully recalculate the balance factor of the ancestor, it is still being disturbed. So for the caution's sake, in case of deletions, even after rotations, either it is single or double, recalculate the balance factor of each of its ancestors. This may happen that for some cases your ancestors still you are not reaching at the root. For some ancestors its balance factor might have been disturbed. That means you may go for some several rotation inside deletion case for its ancestors. So still it is has been disturbed. Now it is -2, just go for the larger height node. Out of 15 and 50, 50 is the node with the larger height node, that is become your y here. And out of this, both 40 and 63, 63 is a larger height node. This will become equal to x. This is z, y, x. This is now have to perform single rotation about that of z. Left rotation about z, the whole of the structure tree will become this one. This is one more example. Deletion of 6. This is not going to disturb the balance vector of this tree. No problem. Deletion of 7. No change in this tree. The deletion of 6. Still no change in this. Deletion of 5. When you're deleting 5, after deletion of 5, you should delete 5 from this. The new structure will be this one. In this case, the pivot node has become equal to 4. That is Z pivot node. If you carefully scan only the node with greater child of this pivot node, that is y, this 2 will become y, and the child node which is of greater height, both have got same height, that which should become the candidate of x. X should be candidate of x because this will lead to single rotation rather than double rotation. The structure will be this one. You have to perform right rotation about the z axis. So right rotation of z axis will lead to this answer. Now moving further, examples, one more example, deletion of 32 in this structure. When you're deleting 32, the balance vector of 44 is being disturbed. This is the Z pivot node, and this is the immediate node which larger child is 78, and the immediate child of Y which is larger height is this is X. So this is the structure is Z, Y and X. You have to perform two rotation. One rotation is right RL here, so right about Y, then after that left about Z node. So this after double rotation you will be getting this as a final answer. Now deletion of 9. Deletion of 9 now in this example will lead to a new structure. If you carefully scan, so this deletion of 9 change the balance vector of the node 5. In this case, this is Z, this is Y and X. Now you will perform double rotation. Again in this case, first this is left right LR rotation. Left first rotation will be left rotation about Y, then right rotation about Z. That is a pivot node. So this will lead to the final tree like this. Similarly, moving further, once you have performed deletion, after applying this double rotation, that is LR rotation, you got this tree, but still the balance vector of its parent node after rotation also, this balance vector of this parent node is still being disturbed. Now we have to again perform one more rotation. In this case, what will the new rotation? If you carefully scan, both the out of 3 and 7, this is Z node, this will become Y node. Out of this y node, the x candidate node will be either 1, 2 and 3. Balance vector 1, 2 and 3 both have got same height, but we have to choose the node with minimum rotation. So this will be the candidate for x. So the rotation for that will be left about z node. So left about z node will be, this will be z, will be y, this will be x. Left rotation about z will lead to this as the final tree. Now this whole of the tree structure is being now balanced in this case. Now if you sum up the steps of this deletion, you just perform the deletion as we did in the binary search tree and find the balance factor of its immediate ancestor of that, the node which has been deleted. And after that, if you find the balance factor of the any of the ancestor node has been disturbed going from the bottom up fashion during that path, then there are different conditions. Four conditions have been there. One for rotation of right child, rotation about rotate right, rotate left, or rotate LR both. Rotate of left, rotate of right of right, left of right. Any of the four rotations can be possible. If you just want to scan it carefully, in this case, when balance factor is greater than 1 and balance factor of the node of left is greater than equal to 0, first case can be this. Now in this case, if you carefully scan, if you're deleting the node, say key value 20 in this case, in this example, so 20 will lead to this structure. Now in this case, this will be z node, this is a pivot node, and node with larger child, this will be the y node, and node further with the larger child of y will be this node. So this is left heavy, so this will be the case of right rotation about z. Now, similarly, if you're deleting the node in this structure, so the 20 is being deleted, so this will lead to this example that that the node to be deleted will be this is the node with the balance vector disturbed, and out of this will be the immediate child of the z which will have larger height. Now both of these children can become a candidate to become x, but we will have to pick this x for our purpose. Reason being, this will lead to single rotation. If you are using the another making this as x, this will lead to double rotation. So we will be picking this x in this case. That means if balance factor is greater than 1, but balance factor of node of left is greater than equal to 0, that is node of left is either equal to 0 or equal to is greater than 0. In either case, you have to perform rotation, right rotation in that case. Second is, if balance factor is greater than 1 and node of left is balance is less than 0, like in this case we are deleting the value 5 here. In this case, node left balance factor is negative, we have to perform RL rotation. That means first this is so LR rotation, first left rotation about this node left, then right rotation about the node. Next is the case of balance factor if it is less than -1. Now in this case, you are deleting the node with key value equal to 10. See, I am deleting this node. After deletion, you are getting this node balance factor disturbs z node, and this will become y, this will become x. This is left rotation about z, one case. Another case, the deletion of 10 will lead to this as z, this as y, and the x, both this can become the candidate of x because both have got same height. But we have to pick this rightmost, leading to single rotation rather than double rotation. So in this case, both cases, when node right balance vector is less than or equal to 0, either it is -1 or equal to 0, in either of the case, we have to perform left rotation. Then next example is this balance vector is negative, like deletion of key 2, balance vector is negative, but node of right balance vector is greater than 0. In that case, we have to perform RL rotation, right rotation about 8, then left rotation about the 4. This is RL rotation which has been written here. Now this is the sum up code we have already discussed. These are the 4 cases. You can go through these one by one. That's all for the session.